So let's plot the u function, or the u of r function, as a function of r, because we know how to deal with the equation for u of r is a familiar equation. So we know that u of r goes to 0 at r equals 0. So this is r, it goes to 0 here, it bends in a certain way, and then it goes to 0 at infinity. Right, those are the two regimes that we're familiar with. And we also know that the Schrodinger equation is really about the bending of the wave function. And so the higher the energies, the greater the bending, and therefore the more nodes we have. So we're going to start to fill in this space. So if we do, let's call it u1 as a function of r, we have a function that qualitatively looks like this, and then comes down and does that, doesn't have any nodes. A higher energy function will have one node, right? We're familiar with that. It goes to 0, comes up, has a node, and then comes to 0 this way. And the next energy level will have to look like this, where it comes down here, it has another node here, and then it comes down above. So we're familiar with this kind of behavior. This is a little bit, it's a little qualitative plot. We understand the zeros at infinity and r equals 0, and then increasing number of nodes as we increase the energy. But of course, the u function is not the wave function. U of r is equal to r times psi, and so psi is equal to u divided by r. And we already saw that the u function is proportional to r to the l plus 1, e to the minus, well, let's call it c times r, right? The c function is minus 2m energy over h of r squared square root. So it looks like that. And so we're dividing by r, so the wave function looks like r to the l, e to the minus cr, and so for different values of l. So if L can be 0, right, if L can be 0, that's a value that's possible. That basically corresponds to 0 angular momentum, right, because L squared, remember the eigenfunctions of L squared, are directly related to this number. When this is 0, then the eigenfunction for L squared is 0, and the squared angular momentum value is 0. So if we have no angular momentum, then L is 0, and r to the 0 is just 1, and so psi of r is proportional to e to the minus cr, and so psi of r equals 0 is not equal to 0. Right? For r equals 0, the wave function doesn't go to 0. So does this mean that psi, let's say, of L equals 0 at r equals 0, psi modulo squared, the probability of finding the particle, well, the probability density, rather, does that mean that, well, this quantity is not equal to 0, right? We're just taking the modulo squared. Does that mean that the probability of finding the particle at r equals 0 is not equal to 0? And the answer to that is no, but there's a little more subtlety because we have to integrate this thing all over all of space, and we'll get something proportional to r when we do that. So we want to be careful there. But it's clear that if psi of L not equal to 0, of r equals 0, this is equal to 0, because then we have an r there, r to the 1, 2, whatever it is, that goes to 0. And so we can see directly that the wave function and the probability density are 0 at r equals 0. And so when we integrate that to find the probability of the particle being in the region near r equals 0, we'll basically get 0.